Alrighty, word on the street is we're live. Hello, hello. Excuse me. Oh, hello. Sorry, hang on. I'm testing to see if we have audio. Alrighty, word on the street. Okay, we have audio. All right, sweet. So we're here. We're chilling. We're gonna get going on lecture in about 5 minutes, and we're here kicking it. There's 7 of us at the moment. So good morning. It's kind of overcast. Totally. Not a bad Wednesday. I apologize for the screen adjustments. There we go. We've got, I don't know about you, but I've been having a pretty chill morning. So I picked a pretty intense song of the day. I don't know if anyone is familiar with the Mars Volta, but song of the day is this wow, bubble in my throat. This apparatus must be unearthed. Must be unearthed. By the Mars Volta. As always, I'll link in the description to Spotify if you want to check it out later. Raj, you've never heard of it. It's weird. It's super weird, but it's super good. It's the type of stuff where like intense study music. I don't know if you like chill study music or if you like stuff that moves really fast, but this is definitely the latter. Excuse me, the whole album. This is off their first album. Really, really good, kind of zoning out, trancing out, but to something really intense. So it was one of my studying favorites back in the day. How are you guys doing? Let's see, we're starting lecture in about a minute. So today we're going to, in lecture, we're going to keep talking about quantum. However, I do want to just make sure I explicitly state that from this point, today's lecture is exam 3 material. So you will not be tested on the content that we go over today will not be on exam 2, but will be make up a decent chunk of exam 3. So the exam 2 cutoff is Monday's lecture. And that's about it. Oh, sweet question. So if quantum is discrete, why do we focus on things between 2 discrete points? I guess I'm having trouble understanding the question. Maybe you could clarify what you mean by quantum being by discrete. Do you mean that that it's kind of the word quantum means it's either on energy level 1 or level 2, but nowhere in between? Because that's what it means to be quantized. It means that there's kind of this like 8-bit stair-step energy level, and there are no possible energy states in between them. So that's actually in the word quantum. That's why we focus on two distinct points. It's because yeah, totally. That's actually built into the definition of quantum. Because there are no energy states in between energy level 1 and 2, that's why we focus on those points. Because that energy is quantized. Does that make sense or answer your question? So for Jesse's question, so we're not going over orbitals like S, P, and D. We are actually today, but that is exam 3 material. So we're actually right about to dive into different orbital types, S, P, and D, etc. But that material won't make it onto exam 2. But yeah, that is, Jesse, the next step that we're moving, that we're hitting in lecture. Alrighty. So, and I'm just taking a quick look. All right. So we've got some material to cover today. Yup. Quantum numbers, principal quantum number, angular momentum quantum number, magnetic quantum number, and spin quantum number. We are hitting those today too. But that means it is exam 3 material as well. Totally. It is cool beans, Jesse. All right, with that, I think we're good to maybe dive in and start talking about some chemistry. All right. So so where we left off in lecture on Monday, we had gone over the Rydberg equation, talked about how great it was. It was an awesome moment for science and mathematics kind of coming together, being able to explain the physical phenomena we saw. That is correct, Raj. Azimuthal is the angular quantum number. So it was a really cool thing. It explained the emission spectrum we saw for hydrogen, but unfortunately, it didn't work for any other element, which sent us back to the drawing board. And we said there were two shortcomings, two flaws of the Rydberg equation. The first, they didn't take into account electron-electron repulsion, which doesn't exist in hydrogen because it only has one electron, but it does for every other element on the periodic table. And then the second flaw is there was an assumption in the Rydberg equation that assumed that's super articulate of me this morning. But there was a built-in assumption that all electrons moved in a two-dimensional circular orbit. And as I said on Monday, that was a decent approximation of the spherical s-orbital that does house a hydrogen's electron, but it was a poor, that assumption did not hold up for electrons in different types of orbitals, that electrons can actually move in 3 dimensions, and the Balmer-Rydberg equation did not account for that at all. All right, and that brings us to the next leap in our understanding of atomic structure, and that is the quantum mechanical model. Now, before we dive into the kind of nitty-gritty of the quantum mechanical model, I want to give us all kind of a user-friendly kind of visualization for what we're talking about. So there are several differences in the quantum mechanical model. Sorry, that's a super fun noise. Hang on. There we go. Several differences between the Bohr model and the quantum mechanical model, but one of the most significant ones is the fact that in the quantum mechanical model, the electron doesn't go in a two-dimensional orbit, but it actually occupies the space of what we call a three-dimensional orbital. All right, and that is where I'd like to start today. So electrons occupy a three-dimensional space called an orbital. These were named kind of in an homage, paying homage to the orbits of the Bohr model. And there are four different orbital types that we're going to talk about, interact with, and I want to give you kind of a visualization of what these things actually look like. All right, so okay, sorry, quick question. Whoops. Oh, there we go. Okay, so yeah, Raj's question: did we cover atomic emission and absorption spectra? Yeah, we totally did. Last lecture with the Rydberg stuff was kind of our introduction to atomic emission and absorption. Yeah, totally. All right, so electrons occupy a three-dimensional space called an orbital, and what this orbital is so what an orbital is it's something called a probability density function. Not probability. So probability density function. All right. Sometimes this is abbreviated as these are called PDFs. All right. Probability density function. And what it is, what this is it's literally a calculated certainty of finding the electron within that space. So there's like, oops. Like a 99% chance of finding the electron within that space. All right, so that's where these shapes come from. The way you should think about them is conceptually is that electrons move so fast that they, I'm going to put this in quotes, fill the orbital. This is one way to think about it. One way to think about it is an electron is like Sonic the Hedgehog. When it runs, it just creates a blur. All right, it moves very, very fast, and as it moves through its orbital, it kind of creates this blur in the shape of the orbital. All right, so you can think of it as this kind of blur, this cloud that the electron is moving through, and it's moving so fast we don't know exactly where it is at any moment, but it's moving so fast that if you were to see it, it would kind of make this glowing, fuzzy shape that I'm about to introduce now. Okay, Raj has a question. What is the difference between orbital and shell? Excellent question. We'll get to that, more into that when we when we talk about the quantum numbers, but the quick answer is a shell equals energy level, and an orbital type is something called a subshell. So on any given energy level, there may be several different types of orbitals, which are called the subshells. But we'll get to that once we get into the nitty-gritty of the specific quantum numbers. All right, so with that kind of idea that the electrons are whirring, they're buzzing, they're moving at such a rapid pace that they make this kind of blurry shape, let's start talking about what shapes these orbitals actually take. And the first type of orbital that I want to introduce is something called an s-orbital. It is the simplest of all orbital types. If you were to draw this in 3 dimensions, so, oops, here, let's get a 3-dimensional coordinate plane up in here. So here, the z-axis is vertical, the y-axis is horizontal, and then the x-axis is coming out of the plane of the page at you. Those of you who've kind of done 3-dimensional graphs of shapes, polyhedra, or maybe some 3-dimensional calculus, this will be familiar to you. If not, again, the z and the y are in plane. That looks like a D. And then the x-axis sticks out like a sore thumb. The x-axis is out of plane. Kind of at you. All right, so hopefully that will help you kind of visualize what we're doing here. Now, the shape of an s-orbital is it's centered at the origin. All these orbitals are, and it's perfectly spherical. All right, so actually, I'm going to clean up this drawing just a little bit. There we go. So the s-orbital is a perfect sphere centered at the origin, and that's the shape that it takes. All right. The s-orbital is the simplest type. It's the one that hydrogen single electron occupies. So the electron around a hydrogen isn't moving in a circle. It's blurring. It's moving around the nucleus at such a rate that it creates this spherical looking shape. All right, so that is the s-orbital. Yeah, the s-orbital is by no means the only type of orbital present in this molecule, or we're not talking about a molecule or atom at this point. We're just talking about orbital types. In addition to the s-orbital, there are also p-orbitals, and I actually should put this as a plural because the s-orbital, so something important to know about the s-orbital is it is non-directional. And what I mean by that is it's a sphere. You can't point a sphere in any direction. It's the same from all angles. So it's non-directional, or you may even call it omnidirectional. The p-orbitals, however, do have directionality, which, as you'll see, will be reflected in their name. So here we have the z, y, and x-axis. And when you look at a p-orbital has a unique shape, again, centered at the origin. And it kind of has this weird dumbbell shape. Now, the p-orbital, like the s-orbital, is 3-dimensional. So both of these lobes of the p-orbital occupy space. The p-orbital has also something called phasing. All right. So you'll notice that the top half is clear and the bottom half is shaded. So we're clear up here, we're shaded down here, and that difference in coloration is known as phasing. Where it comes from is it's just an artifact of the differential equation that you solve to get these shapes, these probability density functions. Half of them have a positive sign, half have a negative sign. And so that the sign of the values that you get when you calculate the probability of finding an electron, half of them are positive, half of them are negative, and that's reflected by the shading or the phasing in the two halves of this orbital. But you don't have to worry about the meaning of that beyond now. I'm including it for the purpose of being complete. For completeness sake, it's definitely part of the orbital, but you don't have to worry about it beyond that. Now, this specific p-orbital, you'll notice, does have a directionality. It's pointed, oriented along the x-axis. Sorry, no, it's oriented along the z-axis, and so it's called PZ. However, it's only one of three different p-orbitals that exist. And if you're wondering why are there three different p-orbitals, well, there's three different axes that we can orient our p-axis along. So this is PZ. PY has the exact same shape as PZ, except it has a different orientation. It's oriented along the y-axis. So this is PY. Now for PX, PX has the exact same shape as PZ and PY. However, the lobes, the two lobes, are oriented along the x-axis, and the x-axis, as we've already discussed, is coming out of the plane of the page, right? Or the board, or the, I guess now, YouTube video. And to show that, when you look at the PX orbital, you're going to be looking at it dead on. And so what you'll see is kind of two lobes stacked on top of each other, one of them clear, and you'll see the other one going out the back. And this is our PX orbital because it's oriented along the x-axis. It's the exact same shape for each of these. They all have the same shape, different orientation. Same shape, different orientation for all of our p orbitals. Cool. Any questions so far? All right. Okay, so that's the s orbital. Those are our p orbitals. Let's take a look at our third orbital type. This is the d orbitals. All right. Now, so the d orbitals, so as you could see on the previous slide, the p orbitals have a more complex shape, a more complicated shape than the s orbital, and likewise the d orbital will have a more complicated shape than the p orbital. The d orbital, kind of, its generic shape, it kind of looks like if you took two p orbitals and smashed them together like this. All right. So like if you made an X out of two p orbitals, that is what a d orbital generically looks like. The phasing looks like so. Each lobe has the same phasing as the lobe opposite it. And again, each of these lobes are three-dimensional in shape. All right, so this is kind of the generic d-orbital shape. But let's actually look at the specific d-orbitals that we have to deal with. So first off, so Z, Y, and X. As you can see by looking at the generic shape, this orbital type also has directionality to it. We can orient it in different directions along different axes. And so that gives, just like we saw with the p-orbital, there are going to be different d-orbitals available to us as opposed to the s-orbital, which is just omnidirectional. Now, the first d-orbital I'm going to draw is called dzy. All right, this is dzy, and it is contained off-axis, but completely in the zy coordinate plane. All right, so we've got phasing. Each orbital opposite has the same phasing as, or sorry, not each orbital, each lobe has the same phasing as the lobe opposite it. This is our orbital dzy. As you could imagine, this is dzy. We can orient, we can pick different coordinate planes to hold our d orbitals. So we can have a dzx as well as a dxy. All right, so we'll be able to draw in those orbitals z, y, x, z, y, x. All right, so the dxy has the exact same shape. Sorry, I'm doing the dzx. It has the exact same shape as dzy, except it's oriented along, or sorry, in the dzx coordinate plane. So it's going to look like this. And then dxy will look exactly the same as the previous two. Just the, whoa, that's ugly. Just our orientation here is along, or sorry, in the xy coordinate plane. All right, so here are our first three d orbitals, but they're not our last three. There are two more. There are two more d orbitals that we can draw. So here, just getting our coordinate planes in line. The first is called dx squared minus y squared. All right. Now, this one, again, exact same shape as all of our other z orbitals. I just called them z orbitals. All our other d orbitals, excuse me. The difference is, with our other d orbitals, the lobes have been off axis, all right? But here, the lobes are dead on axis. One of the lobes is oriented along the x-axis. And the second two lobes are oriented directly on the y-axis. So it'll look like this. Again, same shape as the others, but here each lobe is oriented directly on an axis. Now, the final d orbital is called dz squared, and this one actually has a different shape than the other four, which is weird and cool. dz squared looks like a giant p orbital with this weird little donut ring around its center. Like that. The donut around the center and the two lobes have opposite phasing, and this is our orbital dz squared. Super cool, super weird d orbital. All right, and these are the 5 d orbitals. Now, with that dz squared, it's kind of the odd one out here. It's a different shape, but the important thing to remember is that all d orbitals have the same energy. So they're equal in energy. Neither is higher or lower in energy than another. Cool? All right. That may have been a drawing challenge. P orbitals, pretty doable. D orbitals, quite a bit harder. And as you can imagine, the f orbitals, we've been getting more complex as we go. The f orbitals are going to be even more complicated than the d orbitals. So let's talk about the f orbitals. The f orbitals are, First off, let me ask you, how many f orbitals do you think there will be? You'll notice that there is 1 s orbital, 3 p orbitals, 5 d orbitals. We're increasing by 2 orbitals of each type as we build complexity, and there are 7 different f orbitals whose shapes are more complex than d orbitals. They're so complex that I would never ask you to draw them. Yeah, totally. There are 7 f orbitals, and they are more complicated in their shape than d orbitals, so much so that I would never actually ask you to draw them. The p orbitals, drawing p orbitals will become very important later as we hit hybridization. D orbitals, they're important to know. I could maybe put that on a take-home portion of an exam, but the f orbitals, I will never ask you to draw because I can't. If you want to see f orbitals, look in your book. There's some really good 3-dimensional renderings, but they're just very, very intense. All right. Now, the point, though, if you're wondering why did we go through this whole song and dance, the reason is this. The energy of an orbital tracks with the complexity of its shape. The more simple complexity, the simpler the orbital, the lower in energy it is. The more complex the orbital, the higher in energy it is. And so one of the reasons why I wanted to give you kind of a visual representation of here are the D's, here are the P's, here are the here's the S, and then the F's are so complex we can't even draw them, is if you can remember that, you instantly have a built-in intuition for which orbitals are higher or lower in energy. So when we compare, when we compare orbital energies, you already, because of what we went through, already know that the s-orbital is lower in energy than a p-orbital, which is lower in energy than a d-orbital, which is lower in energy than an f-orbital. All right? And as you'll see in the future, having that intuition will pay dividends. All right? So orbital energies track with orbital complexity, the complexity of those shapes. All right. Now, one last thing that I want to kind of communicate to you, and this is something that we'll be coming back to, is the idea, and this actually will touch on a question that Raj asked earlier. What's the difference between orbital and shell? All right. When we talk about shells, shell is super important. When we talk about shell, what shell an electron's in, we're talking about the energy level. All right, we're talking about the energy level, and this is, you'll recall from the Bohr model, we labeled every orbit energy with the variable n. All right, so we said that there's the first orbit energy, which is n equals 1, and then n equals 2, n equals 3, etc. And those were moving farther and farther away from the nucleus. Now that continues to be true in the quantum mechanical model, but as you can imagine, there's a decent level of complexity that builds up as well, because we're not just talking about concentric circles moving farther and farther. We have all these different orbital types, and the shell, or the energy level, determines how many different types of subshells you can have. So what energy level you're on, what shell you're on, determines whether you have an s-orbital available, p-orbitals available, d-orbitals, f-orbitals, etc. And I want you all to have this in your notes, because this will be a very useful kind of tool, visual aid, as we move through, the remainder of this chapter and even into chapter 8. This is going to be a useful kind of thing to have in your notes as you work homework problems, etc. So first, you should know that on the first shell, energy level equals 1, there is only one s-orbital. All right? On your first energy level, there's only one s-orbital. As you bump up to the second energy level, all right, so second shell, you have one s-orbital and you have 3 p-orbitals as well. All right, so on that second shell, there are 2 different subshells, s and p. On the third energy level, there is one s-orbital, 3 p-orbitals, and 5 d-orbitals. Finally, on the fourth shell, there's 1s, 3p, 5d, and 7 f-orbitals. All right, and on every shell above 4, you have all 4 subshells available to you, s, p, d, and f. All right, so I wanted to kind of get that in your notes. We can keep that in mind as we move forward and start talking about the quantum mechanical model of the atom. Or let's see. Okay. All right, let's pop open a new slide. Okay, so we're about to move into the section of the chapter where the quantum mechanical model, where things get a little more abstract. All right, and again, I gave this disclaimer at the beginning of the chapter, and that is that we have in the quantum mechanical model that this comes to us as a byproduct of a lot of calculus and differential equations. All right, which is, we're not going to get into the actual mathematics of where this stuff comes from. We're more going to focus on the meaning kind of these different kind of pieces of the puzzle. All right, and first off, when we talk about the quantum mechanical model, of the atom, there is one fundamental assumption that kind of undergirds this whole concept, and the assumption is that every electrons are waves. Or we talked a little bit when we introduced light about how that in this course we're going to assume that all lights are waves, and we said that even though everything in the universe has particle wave duality, the less mass something has, the more wave-like it is, and light has no mass, so it's the closest thing we have to a pure wave. Well, electrons have a very, very, very small mass. They're much smaller than protons and neutrons, and even though they do have mass, because it's so small, their behavior is largely wave-like, and so this assumption is a good one. All right, the quantum mechanical model assumes that every electron is a wave. All right, it treats each electron as a wave, and then it proceeds to describe it. It describes something called the because it assumes every electron's a wave, every electron has what's called a wave function. All right, wave functions these are differential equations with 4 parameters. All right, and we'll talk about what each of those parameters are. Raj actually already dropped an Easter egg up in the comments. We'll be getting back to that in a little bit. So wave function is a differential equation with 4 parameters, and in the quantum mechanical model of the atom, each electron orbiting an atom, or I should say a nucleus, has a unique wave function. i.e. 4 different parameters. All right, we will explore what these parameters are and what they mean. But before we do, I just want to kind of set up conceptually. These are 4 different parameters that belong to an electron's wave function. They tell us something about the electron, and every electron that's orbiting the same nucleus, I said A right here. I'm going to edit this in. Orbiting the same nucleus has a unique wave function, i.e. 4 different distinct parameters. Cool? All right. Now, let's talk about what these parameters are, what they mean, and then we'll move and start talking about exam 2. All right, so the first parameter that we're going to discuss is called the principal quantum number. The principal quantum number, which is abbreviated with the variable n. All right. So the allowed values for n. N can be any integer starting from 1. So 1, 2, 3, 4, ... It goes on. And n, the principal quantum number, describes the energy level or shell of the orbital. All right, the energy level or shell of the orbital. So, with this information, I could ask you, for example, to consider 2 electrons. I'm going to call this electron number 1. I'm going to call this electron number 2. And if I told you that electron number 1 was in the first shell and electron number 2 was in the third shell, I could ask you which is closer to the nucleus. All right, which electron, number 1 or number 2, is closer to the nucleus? Ooh, a long, awkward pause. This may be a result of some lag. There we go. Which one's closer? Awesome. All right, Vraj, number 1. Totally. Number 1 is closer to the nucleus, but the question is, how do we know? All right. Well, when you think about it, n tells you the energy level of the orbital. Yeah, totally, Macy, straight up. N tells you the energy level, right? Whether it's lower energy or higher energy. And an electron wants to be as close to the nucleus as possible. As we talked about with atomic emissions, right? When you move the electron away from the nucleus, that's an endothermic process. It requires energy. An electron moving closer to the nucleus is exothermic, releases energy. So the lowest energy state is also going to be closest to the nucleus. Lowest energy is closest to the nucleus. All right, so that's one. So that's a example. The higher the number, the higher the distance from the nucleus. Yep, that is 100% correct. So there's an example of how you can use this conceptual information to kind of answer questions, solve problems with the meaning behind these quantum numbers. That is the principal quantum number. Let's move to the angular momentum quantum number. Angular momentum. All right, the angular momentum quantum number is the symbol for it is a little lowercase cursive l. All right, and the allowed values for the angular momentum quantum number, it can be any integer. The lowest possible value for L can be 0, and it ranges. So there's a range. The lowest possible value is 0. Its maximum value is actually determined by the principal quantum number. The largest value that L is allowed to have is 1 less than the principal quantum number. All right. The angular momentum quantum number defines the three-dimensional shape three-dimensional shape or subshell of the orbital. Okay. So Raj just asked the question, what is the maximum number of electrons allowed in one shell? I will answer this in one question. So here, hang tight. Oh, yep. He just asked, is it, wait, no, hang on. Is it 2 times the number? 2 squared. Wait. No. Here, hang on. I'll answer this in one sec. Let's finish up with the angular momentum quantum number, and then we'll answer that question. So I just said that L is defines the three-dimensional shape or subshell of the orbital, and here's how. All right, here's how. So I'm going to make a little graph showing L and subshell. So when the value for L is 1, let's start at 0. If L equals 0, that means the subshell of the orbital holding the electron is an s-orbital. When L is equal to 1, that means the electron is in a p-orbital. When L is 2, it's housed in a d-orbital. And when L is equal to 3, it's housed in an f-orbital. So by looking at the angular momentum quantum number, you can instantly know what type of orbital your electron is being housed in. Now let's combine this information with what we know about the allowed values for L. All right. So let's talk about the first energy shell. If n equals 1. The allowed values for L, lowest possible value is 0. Maximum value for L is 1 less than n. Since n is 1, on the first energy shell, there's only one possible value for L. That means that there is only an s-orbital available. All right. What about the second energy level? Well, the lowest possible value for L is 0 on the second energy level. The highest possible value for L is 1 less than n. So L's minimum is 0. Its max is 1. That means that the possible sorry, I start talking like Sean Connery. The possible subshells. The possible subshells on the second energy level are S and P. All right. When you look at the third energy level, our minimum value is 0. The maximum is 2. So L can be 0, 1, or 2. That means that our possible subshells on the third shell are S, P, and D. All right. And then on the fourth energy level, n equals 4. L's maximum value is going to be 3. So the possible values will be 0, 1, 2, and 3. Which means that on the fourth energy level, the electron could be in an S, P, D, or f orbital, all available on the fourth energy level. All right. Now, with what we know about the angular momentum quantum number and the principal quantum number, we can now solve problems that look like this. So consider consider the following 4 electrons. Consider the following 4 electrons, where the first has a principal quantum number of 1, angular momentum quantum number of 0. Second, principal 4, L0. Third, principal 2, angular 3. And fourth, principal 3, angular 2. I could ask you, for example, there we go. Which wave function describes an electron that cannot exist? All right, which describes an electron that cannot exist? All right. So when we talk about, which one can't exist, we're asking which set of numbers has a non-allowed set of quantum numbers. And we know that n can be any integer starting from 1. So when you look at all your options, n totally checks out, right? They're all integers ranging from 1 to 4 here. But we also know that L, the allowed values for L, are only L's minimum value is 0. So we know that these two are good. its maximum value is 1 less than n. So here, 2 is less than 3, so that's okay. But when you look at number 3, this is a disallowed value because L is actually never even allowed to be equal to 3. And in this example, it's greater than, sorry, it's not that L is not allowed to be equal to 3. L is never allowed to be equal to n, and in this case, it's greater than n. So in this third electron, this wave function cannot exist because L will always be maxed out at 1 less than n. All right. Now, Raj, the answer to your question. So here we've got. Yeah. Oh, hang on. Here we have a question from Raj in the comments. And the question is, let me scroll back. What is the max? What is the maximum number of electrons in one shell? Which is an excellent question. The answer, so that is the question. The answer depends on the shell. And the reason this is it depends upon the shell because it depends upon the number of orbitals available. Something we'll be talking about probably next lecture is sorry, it just hit me that I have an exam scheduled, but we're going to be lecturing. I'll talk about that at the end. So depends upon the shell. Something that that we'll talk about next lecture is that each orbital holds 2 electrons max. All right, so each orbital holds 2 electrons max. And so if you look at the first energy level, there's only 1 s-orbital on the first energy level. So on the first shell will hold 2 electrons. On the second energy level, L can equal 0 or 1. All right, this means that we have 1 s-orbital, 3 p-orbitals, and so we've got a total of 4 orbitals, 2 electrons each. We can hold 8. When you look at the third energy level, L can be 0, 1, or 2. That means you've got S, P, and 5 d orbitals. So the third shell can hold 18 electrons. Finally, on the fourth, we have L is 1, 0, 1, 2, and 3, which means that we have S, P, D, and F. Which gives us the capacity of 32 electrons in that shell. And then every energy level above the fourth energy level holds 32 electrons. So that's Raj, that's the longer or more complete answer to the question that you posed earlier. All right. So, where are we? It's 12:30. Okay. We've got two more quantum numbers to talk about, and then we will be good to start talking about the test. Okay, so let's talk about, so we've talked about the angular momentum quantum number, the principal quantum number. The next is called the magnetic quantum number. The magnetic quantum number is has a symbol m sub L. It is a lowercase m with a subscripted cursive L. The allowed values for the magnetic quantum number, the allowed values are a range, and the lowest, they're all integers, the lowest allowed value for m sub L is defined by the angular quantum number itself. It's negative L. M sub L can be any integer ranging from negative L, including 0, and then maximizing out at positive L. So the value for L determines the range of M sub L. And M sub L, we know that N tells us the shell, L tells us the subshell. M sub L defines the spatial orientation of the orbital housing the electron. All right, so M sub L tells us the orientation of said orbital. So, for instance, if you consider first shell, the only possible value for L is 0, right? Because the maximum value is 1 less than n. And if L is 0, there's only one possible value for M sub L, which is 0. All right? And the reason there's only one value, there's one value because the s-orbital, the s-orbital has no orientation in space. All right, the s-orbital has no spatial orientation. Let's talk about, let's compare this to if we have n equals 2. Now, L could be 0, right? But L could also be maximum value positive 1, right? 1 less than n. If L is 1, then M sub L could be negative 1, or 0, or positive 1, right? And when you remember what L equals 1 means, this means we're dealing with a p-orbital, or I should say p-orbitals. Right? And p-orbitals have 3 spatial orientations. Right? P-orbitals have 3 spatial orientations because there's px, py, and pz. So those funky subscripts that we saw when we were drawing out p-orbitals actually come from emps of L. All right, there's 3 different orientations for the p-orbital, and that's why there are 3 different distinct values for your magnetic quantum number. All right, you'll notice that if you do this same exercise, let's say n equals 3, L equals 2, you look at your d-orbitals. If L is 2, there are 5 possible values for emps of L. -2, -1, 0, 1, and +2. 5 distinct values because there are 5 distinct d-orbitals. You can also do this for the F block as well. Now, you don't need to memorize, like, don't take this the wrong way. I'm not writing this up here to say memorize that emps of L -1 is px. That's not what I'm saying. What I am saying is the 3 distinct values are there because there are 3 distinct p-orbitals, just like when L is 2, there are 5 distinct values for emps of L because there are 5 distinct d-orbitals. Does that make sense? All right, that is the magnetic quantum number. Let's take a look at the 4th and final quantum number, which is the spin quantum number. All right, the spin quantum number has a symbol of emps of s, so it's a lowercase m with a subscripted s, and the spin quantum number has the following possible values. It could equal +1/2, or it could equal -1/2. Those are the 2 distinct, the only 2 allowed values for emps of s. All right, and the reason why this is here, I'm going to give you kind of more the blue color reason. What emps of s actually tells us is it tells us the orientation of the magnetic field generated by the electron as it moves through space. All right, that's not something you need to memorize. That's not something that I'm going to test you on here. That's something that if you end up taking physical chemistry in the future, you'll spend a lot of time, wonderful time, delving into the rich meaning behind that these fields are vectored quantities and they have different orientations, and it's awesome, but that's not this class. The kind of blue collar way to approach the spin quantum number is this is how you tell. So you'll remember at the beginning of this section, I said that each electron orbiting the same nucleus has a unique set of quantum numbers that are different from the set of quantum numbers of every other electron, right? They each have a unique wave function. The spin quantum number is how you tell 2 electrons that are on the same shell, and on the same subshell, and in the same orbital. In the same orbital apart. All right, key thing to focus on, how you tell 2 electrons apart, all right, that are on the same shell, in the same subshell, in the same orbital, all right? So, for example, let's consider an atom of helium, all right? Helium has 2 electrons. We call this electron 1, this electron 2, all right? Now, both of these electrons have a principal quantum number of 1. They have an angular momentum quantum number. Since their principal quantum number is 1, their angular momentum quantum number must be 0. That's the maximum value. If the angular momentum quantum number is 0, that means there's only one possible value for the magnetic quantum number. It must also be 0. Now, if each of these electrons are going to have... Sorry, hang on. Let me try that again. Each of these electrons are on the first energy level in an s-orbital, right? And they're in the same s-orbital. That's what the m-orbital tells us right here. They're in the same s-orbital. All right. But we know that each one needs to have a unique wave function. It needs to have a distinct set of quantum numbers, and that's where m sub s comes in. The m sub s for one of these electrons will be a positive 1/2. The m sub s for the second electron will be a negative 1/2. It doesn't matter which one you give the positive or negative to, but they will have different quantum numbers. Oh, Macy, you think I missed a word? Let me take a look. How you tell two electrons that are on the same shell and on the same subshell and in the same... Oh, you're right. I did. In the same what apart? In the same... How about the same orbital? Awesome. Thanks for that catch. All right. So that is the spin quantum number. All right. Yeah. Orbital is the word I missed. Okay. That is where I want to stop lecture today. And let's talk about the second exam. All right. Exam 2. All right. So here's something that literally just hit me while we were... What is... Oh, okay, sorry. Raj has a question about spin. What is parallel spin? So parallel spin... We say that two electrons have parallel spin if they have the same electrons have the same m sub s. I should say same value. Same value for m sub s. That is parallel spin. Now, based on what I just said, you may be thinking, but that's not possible, right? How can you have the same value for m sub s? Well, you can't if you're in the same orbital, but you can if you consider the following 3 electrons. E1, E2, E3. I'm going to put all of these in the second shell. I'm going to put all of them in... Whoa! There's no p quantum number. I'm going to put all of them in the first subshell. All right. But I'm going to give them all different m sub l's. I'm going to call this -1. I'll call this 0. I'll call this +1. positive 1. All right. So you'll notice that here, these are all in different p orbitals. One of them's in px, one of them's in py, one of them is in pz. All right. And now I'm going to say m sub s for the first one is plus 1/2. M sub s for the second one is plus 1/2. And m sub s for the third one will also be plus 1/2. We would say that these 3 electrons have parallel spin. They have parallel spin because they have the same value for m sub s. Does that make sense? Okay. Okay, so that is Roger's question with parallel spin. We've got a couple more trickling in. Sarah, would you ask us to figure out the spin quantum number? And can we tell? I mean, I would. Sorry, I'm live streaming from the office in our house, which is on the first story, and we have a labradoodle who just poked his head up in the window and was like, I hear a voice. So would I ask you to figure out the spin quantum number? I mean, I could probably cook up a problem where you'd have to determine the possible value, like if I could imagine, but basically picking a spin quantum number is pretty easy. It's either plus 1/2 or minus 1/2, right? And if an electron has the same principal quantum number, angular quantum number, and magnetic quantum number as another electron, let's say that electron has spin plus 1/2, then there's only one possible value. You have to give it minus 1/2. So I could figure out a way to couch a problem like that. It wouldn't be too bad. All right, let's see. So that's Sarah. That's hopefully the answer to your question. Okay, Diana. So when it comes to the 2 electrons, the m sub s is plus or minus 1/2, saying they are spinning in opposite directions. Yes, Diana, that is 100% correct. The reason why it's positive and negative is because they are spinning in opposite directions. Specifically, the orientation of the magnetic field created by the motion of the electron have opposite signs. So you know how magnetic fields can have like north and south pole. It's kind of similar to that concept. So they have opposite orientations. That's why it's positive and negative. Up or down, totally. All right. Hopefully that answered the spin questions. All right, let's talk about the test. So, I made an announcement that I was moving exam 2 to Monday, March 30th, and I didn't realize at the time because I'm still still adjusting to this whole digital zone. Normally I give exams during class, right? So we have to hold an exam on a lecture day. However, we're not like doing that now, right? And I can actually see, so this is so far been the lowest, we've had the lowest number of viewers on this live stream, and I'm guessing it's probably because I said that exam 2 would cover everything we lectured on through Monday, but what I was lecturing on today wouldn't be, that material wouldn't be on exam 2, it would be on exam 3. Oh, Sorry. Sarah has a question. Let's see. Not related to today's lecture. Okay. Okay, Sarah, hang on one second. I will get to your question. Let me just finish with this. So, I realized that I had announced that we're going to be holding exam 2 on Monday, but then we also have lecture scheduled. Now, I'm obviously not holding the exam in lecture, and so I can imagine that if I said you'd have 24 hours to complete the exam. That if that were the case, if you had to finish the Canvas and the take-home exam, probably no one would want to tune in for lecture because the exam's more pressing and the content covered wouldn't come into play until the third exam. So it'd probably get a decent number of rewatches, but it wouldn't be the most effective data live stream. So as a result, I'm planning on pushing back the exam to Tuesday. That way you don't have to feel this crunch of oh, do I watch lecture but it's not on the exam. The exam's today. I've got to get that thing done. So rather than sitting in a room and talking to myself, I'm going to push it back by one day. So exam 2 will be held on the 31st, again, of this year. So we're going to push it back to the Tuesday, is when I'll be opening the Canvas quiz and sending out, I'm a goat, sending out the take-home. So we're bumping it one day. That way you don't have to decide oh, do I watch live so I can ask questions, or do I just save my questions for later? All that jazz. So we're pushing it back one day. Now, normally when it comes to reviewing for the test, I've got very specific points breakdowns. Here's what you should expect from here are the concepts. Here's the specific percentage points that each one's going to have, and I have approximate values, but these aren't hard and fast because I'm still working on building the exam. So it's not completely done yet. I've made more progress on the Canvas part because that one takes more work because I'm building up a problem bank. Is the homework still due the 30th though? Sarah, that's a great question. So I'm bumping the exam back by a day. Let's just make it all do the same at the same time. So what is this? I believe it's homework 5 and 6. I'm just checking real quick. Yep. So exam 2, and we'll also say that homework 5 and 6. We'll make that do the same day, just to simplify things. Sarah, awesome question. Hadn't even crossed my mind. So we'll make all of that do all at once. I'm going to need to write this into I'm going to write an announcement on our Canvas page for anybody who is not watching, but I need to write myself a note. Otherwise, I will totally forget. Okay. So for the canvas, post, due dates, all right. So we're bumping the due dates there. Now, okay. So here, let's talk about points breakdown. For exam 2. Ooh. All right, so points breakdown. So first off, let's talk about canvas. So this will be timed. Again, I might tweak it at the end of it, but as for now, the plan is 40 minutes, multiple choice, and as of right now, the plan is 30 questions. These aren't going to be long. They're going to be short. You may want to have pencil and paper at hand to like work some stuff down, and your calculator. Multiple choices. I would recommend. I'm going to be. I would recommend printing out the equation sheet that'll have the equations and constants, and just having that while you take the multiple choice exam. Obviously, it's just like the take home. It's open book, open internet, open other humans. But due to the fact that it's 30 questions, 40 minutes. These are going to be shorter questions and questions that you're just going to want to bang out. So if you're flipping through the textbook looking for equations, you're going to be losing valuable time and it may hurt your score. So I would recommend having the equation sheet at ready. Okay, Lauren has a question. Do we have 24 hours to begin the multiple choice, but once it's open, that time begins, or is it scheduled? Okay, Lauren, great question. I am going to open the quiz. The quiz will be open for 24 hours. Yes. So there's no set time you have to log in and take it. It's once you log in to take the quiz, you'll have 40 minutes from that login time. But you can choose to do that at any time you want. Totally. So 24 hours to take it. 40 minutes once you start. Yeah. All right. So, again, this is not the kind of, I'm taking two approaches. This is one, they're short, they're quick. Do you have that base knowledge of information where you can just sit out and bang out a bunch of problems? You can hear me snapping. Where can we find the equation sheet? Excellent question. I will, it will be on the, page 1 of the take-home exam. So, Macy's question, where can we find the equation sheet? Just like any of my other tests, the first page of the take-home will be the equation sheet. So you can just print up that first page to have with you, or have it on your computer screen, whatever you prefer. Okay, cool. So now with the Canvas exam, I have the most specific information. And so there's going to be three sections. The first one is going to be gas laws, which the gas laws will be made up of combined gas law problems, ideal gas law problems, and Dalton's law of partial pressures. So these are kind of all... Ooh, that's ugly. It's a little better, maybe. So the gas laws, you'll be dealing with these three concepts, and you can expect that for the Canvas multiple choice, that this will represent, let me see, about 30% of the Canvas quiz. There's going to be, let's see, question. In the multiple choice, are we allowed to jump around through the questions, or is it once we submit, we can't go back? Okay, so I believe, and I'd have to double check with this one, but I believe that for the multiple choice, the way it's set up is that you can select any question, so it doesn't have to be worked through. I believe I have it set up so that you don't have to work through it in a linear fashion. But once you submit an answer, it's done. There's no multiple submission. So it's one submission per question, but you can go to like question 1 or question 2 or question 3, if that makes sense. Will there be a chapter 5 worksheet? As of right now, okay, so Sama has a question. Will there be a chapter 5 worksheet? As of right now, there won't be. Normally, I do put out some sort of like chapter 5, like here's some questions that I've written on chapter 5 material, just to give the whole class an example of how I write the gas law problems. But as of this moment, I'm not going to be able to, and the reason why is with the whole move that we had to make from physical instruction to online instruction, it's just soaked up every bit of spare time that I have. I'm still grinding away to get the exam up and running because I'm having to make multiple versions of the take-home and generate a problem bank for the online quiz. So I don't actually see myself being able to put together a chapter 5 worksheet. That being said, part of the reason why I would do a chapter 5 worksheet in during previous semesters is that the types of problems that I write, as you know, can be a little more intense than the homework problems you find in the book. And under the time crunch of having to take an exam in 80 minutes, it's useful to see those beforehand and get some practice. Now, what kind of solves that problem is the format that testing is taking in this kind of digital realm. One, the problems that are in the multiple choice are not going to be like my difficult styled problems. They're going to be very straightforward, quick multiple choice, crunch these numbers type of a deal. Very similar to what you run into in the ACS. So I won't be getting creative with the multiple choice problems. Now, I will be getting creative with the take-home exam problems. But again, because they're take-home exams, you're going to have 24 hours to solve them. So there won't be the time crunch. So hopefully not having a Chapter 5 worksheet made this semester, hopefully that won't impact things too negatively. But anyways, I apologize for not being able to get that out, but it's just with the time constraints we have in this new digital age, wasn't able to get that done. So we are going to have gas laws on the Canvas exam. There is going to be a thermochemistry section. Which should not come as a surprise. And for the thermochemistry section here, we're talking about things like calorimetry, right work, delta E and delta H, Hess's law, standard enthalpy of formation, that sort of thing. These, all right, so we'll all up in the thermochemistry section, will comprise about 50% of the Canvas stuff, and then finally there's going to be a little bit of quantum, right? Mostly the stuff we talked about with light, and some Rydberg emission stuff, and here, so this will comprise around 20% of the Canvas exam. So it'll be thermo heavy, 50%, 30% gas, 20% quantum, and that's what you can expect on the Canvas portion of the test. Let's see. Do you think 40-minute is time crunch for 30 questions generally, or more than enough time considering the difficulty level of the questions? Okay, Sarah, that is an excellent question. So the question being that will 40 minutes be enough time to take to solve these 30 questions? And the answer is the types of questions are going to be short and quick. They're not going to be these large complex problems. They're going to be similar to the ACS homework, and that they're going to be small, straightforward, kind of just bang them out really fast. This portion of the exam will test your basic knowledge and how well do you understand your basic knowledge. So do you have the ability to sit down, crunch through these problems, or if it's taking you a lot of time, do you not have a good command of kind of the base level, the introductory types of problems? So to answer your question, though, will 40 minutes be enough time? Part of my evaluation as I build the questions in this problem bank will be once I have the problem bank filled out and can kind of take a few practice quizzes, practice exams myself, I'll be evaluating, is 40 minutes enough time? If I don't feel that it is, then I'll add more time to the quiz. If I feel that it is, then it'll stay placed. But for right now, the plan is 40 minutes, 30 questions. If the 30 questions difficulty levels merit more time, then I'll add more time to the quiz. But I think you should expect to, I think you should expect to feel a time crunch for the Canvas portion of the exam. I imagine that most everyone will feel a time crunch, and it's kind of two different testing modes. The testing mode for the Canvas portion will be simple problems, but not a lot of time, so there's a time crunch there. The take-home will be difficult problems, but you'll have, quote unquote, all the time in the world. You'll have 24 hours to solve them. So easy problem level, hard time level, versus hard problem level, easy time level. That's kind of the testing strategy that I'm going with. Hopefully that makes sense. So that's the Canvas points breakdown, or rough points breakdown. Now for the take home, and most of my focus up to this moment in time has been on the on getting the Canvas problem bank filled out. So I've spent the least amount of time on the take-home exam, but I have done some work. I've got a rough idea of the structure. I will have more I will know more come Friday, and actually with the exam now bumped to a Tuesday, I can also weigh in with even more certainty if you have any specific questions about it on Monday at the end of class. But here's what I know at this moment in time about the take-home exam. As you guys all know, on exam 1, the redox problem, nobody did well. So on exam 2, you will have to work the same type of using the half reaction method to balance a redox reaction. There will be gas laws. There will be thermochemistry. And there will be light stuff. Again, up until Monday's lecture is the cutoff for exam material. Now, the percentages here, you can expect that about 10% of the take-home exam will be redox. About 10% of the take-home exam will be light. And around 50% will involve gas laws. Around another 50% will involve thermo. Now, adding these all together, this adds to 120%. What does that mean? And that means, as you already know, that some problems involve multiple concepts. All right, so what that means is you could expect that maybe there's a problem that touches both gas laws and thermochemistry, or maybe there's a problem that touches both thermochemistry and light. There could be all sorts of combo problems. Maybe it'd be possible for a problem to involve gas laws and thermochemistry and light. Like maybe we could write an omni problem that has all of these interlocking parts. Who knows? Anything's possible. But you should definitely expect involved problems that you're going to sit down and have to work through, and maybe use your textbook, your notes, pool some brain juice with a friend. Who knows? So anyways, that's what I know right now. Again, these are rough approximates. These aren't the hard and fast numbers. Once I have the exams finished, I will be posting the exact points breakdown percentages. But these are based on kind of the rough drafts that I have going on in the works, what things will look like. Again, more certain on the Canvas. The take-home has gotten the least amount of attention so far. But once I finish filling out the problem bank, I will take some time to kind of lock that take-home exam down. Cool? Okay, any questions? Questions and or concerns? You need a monster. Either a monster energy or maybe a werewolf to come track me down and eat me alive. It's going to be challenging. I have a my brother is staying with us. His college situation also got shut down, and he just finished taking a midterm, and it was a take-home thing. He had 24 hours to do it, and his mood just rapidly degraded as the day went on because the problems were so. He was like, "Oh, these problems are so hard. They're just so much harder than they would normally be." And as I was watching kind of his struggle, I was thinking, "Ooh, people are going to probably be cursing my name in the same way." Let's see. Does the Canvas part tell you the grade when you finish? Okay, Sama wants to know whether the Canvas portion of the exam will tell you the grade when you finish. And yes, it gets graded instantly, entered into the Canvas gradebook, so you'll know how that went once you're done. So at least that part will be kind of immediate and instantaneous, and then with all of the take-homes, I'm going to get, my inbox will be flooded with emails, and I'll have to take them, download them, grade them digitally. I will be returning them to you, in case you're wondering. I'm going to be grading them on my Surface. So you'll be receiving your exam back exactly as you would have had we been able to meet, because I'm just going to write directly on the PDFs and correct them. You'll see the points breakdown and all that jazz. So my hope is, well, not hope, my hope. I can tell you that part of it will be normal. It may take me a little longer to grade because for an in-class exam, everyone has the same version of the test, but there's going to be a few different versions floating around. So it'll be like grading like 3 or 4 different tests. So it may take me longer because I won't start sending them back till everyone's are graded. So everyone will receive their grade at the same time, and then I'll upload them to Canvas. Does the Canvas part have extra credit? The Canvas part does not. So as you know, I always build a little extra credit into every test that I give, and the Canvas part will just be 60 points, straight up 60 points. The extra credit portion will be built into the take-home. Totally good question. Are there others? Oh, sorry. Every once in a while I accidentally thwack my microphone. All right, well, something to keep in mind is, so even though the exam is, oh, here, let me see. If you make the test an assignment on Canvas, I think it would be easier for you so you don't have to go through your email. That's yes. Okay, so Sarah said if I made the test an assignment on Canvas, it'd be easier so I wouldn't have to go through my email. That's correct. But the thing about it is, if I did that, then every student would receive the same test, I believe. And at least for right now, for the take-home portion, I'm writing several different versions of it. And so to distribute the different versions to all of you, it's going to require me to send a personal email straight from me to you. So again, this is something that I'm trying to figure out, because I'm as new as I guess all of you are to this whole online education thing. It may be in the future that this proves like too much of a hassle to be able to do the whole take home exam thing. So for future for future tests, future sections, I may be tweaking the format. I might also, depending upon how this goes, I might change the format that I may change the format of exam 3 based on how exam 2 goes. So everything is, at this moment in time, everything's an experiment. Everything's kind of fluid and under evaluation. I've never used Canvas as a testing platform before. And so I thought, rather than do a pure take-home, maybe give the Canvas portion a try, which is why I'm splitting this thing half and half. Maybe I'll really like it. Maybe you'll really like it. Maybe exam 3 will be pure digital, no take-home component. Maybe the take-home component will be too much of a hassle. We'll see. We're all trying to figure this out together. So, it's possible that I may go that route in the future, but for now, I'm going to roll with as I've laid things out, and then evaluate it at the end, see how it goes, see if we want to change things up for exam 3. Totally. But thank you so much for the heads up that it is possible to use Canvas to distribute tests and stuff. Cool. Okay. So, and hit me up with more questions. I'm still here, but I'm also going to start wrapping things up. Something to keep in mind is we have office hours this week. Office hours are each Friday, including this Friday. Fridays at 1. All right. This is a great opportunity to get your questions in as you're doing homework, as you're studying for the exam, things that you may not, things you may be struggling with or want a little more clarification on. Email these into me. You can email them or send them through my to my Canvas inbox. And remember to do 2 things. You want your subject line to read Chem 400 office hours, because I'm now hosting a office hour for my Chem 420 section. So make sure you got Chem 400 office hours in the subject line, and then include a pic of the problem itself. That way I can kind of line them all up and we can make the video as streamlined as possible. All right, so do those 2 things. We'll be able to answer all your questions. Yeah, so that is that's lecture for this week. I'll see you all, or some of you, on Friday. Hopefully I don't have you too spooked for the exam. Yeah, we'll see how it goes. Mostly I'm just in a crunch, because setting up the kind of digital thing takes a lot more work than normal. So So I'm not under the gun, but just, grinding through, getting things all ready, and we'll see how this experiment goes. Thanks everyone for joining in. Your questions have been awesome, and I will see you all, or some of you possibly, on Friday.